So I'm glad Thomas did a general introduction on fabric inheritance, so I'll get to skip that. And so in this talk, I'd like to discuss the nature of the crust in Southeast Asia, which is somewhat different from the crust of Europe or Africa, in that it's newer crust, it's tectonically very dynamic, and so there's a lot of younger fabrics in this crust that say you wouldn't be seeing in Africa, for example. So we'll take a look at the types of crustal inherited fabrics in Thailand rifts, and then some general models. So these are the Cenozoic rifts in Thailand. They occupy quite a large area of Thailand. I'll focus mostly on this central belt, but note there are these rifts out in the Andaman Sea as well. And the location of Thailand is here in a region of collision with the Himalayas, subduction here, and there's collision of Australia with Southeast Asia down here. So tectonically, this is very dynamic with considerable stress changes through the Cenozoic, giving rise to multi-phase rifting in places. And I should point out the data we have from outcrops, there's some coal mines, satellite images, as well as industry data. Okay, so the Southeast Asia crust began to be assembled during the Asinian collision, orogeny, which is during the Triassic. And so there's some sketches here of the blocks that I'll be talking about. So Cebu Masu here, the Paleotethys, which is the future Inthanon zone, the Island Arc terrains, the Sukhothai Arc, and the Indochina terrain. And so in the late Triassic, this ocean closed. There was collision of these narrow continental fragments. So in a way, it's somewhat analogous to these East African rift setting, except this is back in we've got Precambrian crust with Cenozoic rifts on it without too much history in between. But small continental fragments, more resistant cratonic areas, and the mobile belts, which focus the rifts. Well, in Southeast Asia, we've got these ribbon continents that act as the small cratons, and then this mobile belt, the Inthanon zone and the Sukhothai Arc. And in blue, these are the rifts. And so you can see that the rifts in Thailand and Malaysia here are very much focused on the suture zone. And this model that Corti et al. Did, the analog modeling here, trying to mimic a cratonic block and a mobile belt, which is weaker than the craton, and then there can be an even weaker zone that really localizes the rifts, or the rifts become wider, where we just have the mobile belt and no particularly discrete, highly weak zone. So if we try to apply that model to Thailand, in central Thailand here, we've got a couple of deep localized rifts, and we'll see what they're localized on in a moment, but they fit this kind of model, whereas the much wider rifts up in the north correspond more with this kind of mobile belt model. So I mentioned that these are small rifts, they're ribbon continents, and Zealandia is a good modern example of a ribbon continent. And what makes them different from normal continental fragments is that they're narrow. The crustal thickness is typically less than 30 kilometers because they've been highly extended throughout the terrain, but locally they're hyperextended. And this is probably a good model for what Cebu Masu and the Indochina continents looked like in Permian times. So if we look at the modern crustal thickness in Thailand, in the west, the crustal thickness is about 30 kilometers or less. There's really only normal thickness crust in this area, in the Karat. And we have the rift system running through the center, but that's not on the thinnest part of the crust. Thinnest part of the crust is over here, and that's inherited from the ribbon continents. Stepping out a bit and looking at the fault patterns in Southeast Asia as a whole, we see the Cenozoic strike slip and extensional faults on this map. And these are some regions where there are low angle normal faults affecting the rifts. And then I'll put this map, which is an elastic thickness map of the lithosphere, corrected for sediment. And what you can see here is that there are localized areas of high elastic thickness, strong crust, and then these areas in blue, which are very extensive of much weaker crust. And we can see that the faults here in Thailand are focused in this area of weak crust and avoiding the stronger crust of the Karat Plateau. So the types of fabrics that exist in Thailand, there's the pre-Indocinian ribbon continent fragments, fabrics developed during the Indocinian orogeny. There are granites that are intruded. Some have a fabric, some are more isotropic in their nature. There's early Cenozoic transpressional fabrics, and then older rift fabrics, older Cenozoic rift fabrics in multi-phase rifts. So the first example, we'll look at the Phetchabun Basin here in just the southern part of this. And this is located entirely within the Indochina block. This is the rift here. And this color denotes Permian carbonates, platform carbonates. These are deep water Permian sediments. Now, sorry, if I run a cross section through here, this is the setting of the Phetchabun Basin. The Permian carbonates here and here, overlain by Mesozoic sediments. In here, this is the deep water Permian section, and that would actually correspond to this kind of hyperextended basin sediment, basin setting that we see in Zealandia. So this zone of weakness was later reactivated by this Cenozoic rift basin. Now, for the Indocinian orogenic fabrics, there are very many of them. There is no metamorphic age older than the Triassic in Thailand, so the crust has been reworked by the Indocinian orogeny. And this basin lies on the back arc suture between the Sukhothai terrain and the Inthanon terrain. So the Pisanulok Basin is lying in this position. And the suture zone takes a very sharp bend in through here. You needn't worry about the different rock ages. These are Permian to Triassic and Jurassic ages. But you can see the overall trends in outcrop and a northeast southwest here, and they bend to north-south here. And as they do so, the rift bends around too. In fact, the rift basically terminates at this change, and the structural fabric turns almost 90 degrees into it. And this follows the back arc suture. This strike slip fault system that developed in the early Paleozoic and has maybe 100, 150 kilometers of displacement on it, offsets the other major suture zone here between the back arc area, the Sukhothai terrain, and Cebu Masa. So we don't see it in this area. So the Pisanulok Basin pretty much matches this kind of model. seismic data. We see low angle normal faulting here. There are carboniferous metasediments here, and the normal faults, which are dipping about 25 degrees here, are following this older fabric. And we have other examples. This one's in the Andaman Sea, again, of low angle fabrics. We can see the faults curving into a low angle to follow these fabrics in basement. And in places, we can map these fabrics out as patches on the seismic data, so we can see where the fabric is. There are some wells, which in unoriented cores indicate these rocks are phyllites, schists, so rocks with a fabric anisotropy, a strength anisotropy, and the dips are about what we're seeing on the seismic. And we have this mixture of low angle faults in brown and high angle faults in black. Most of the low angle faults are dipping to the east, as are the fabrics. And when we look at the major bounding faults of all these basins through here, we see that their dip angles vary between 60, as you'd expect for normal faults, and much lower angle dips between 20 and 30, which, as we know, occur in some normal faults, but it's mechanically difficult to get them to do it. So we need a special reason why the faults are doing that. And here, when we split the faults up into west and east dipping, we see the west dipping faults are relatively high angle and mixed with the east dipping, and only the east dipping faults are low angle, indicating it's the east dipping pre-existing fabrics that are influencing those faults.
Chris, sorry,
and this in turn, sorry?
10 minutes are over. You
okay?
Yeah, just to
thank you.
Know.
So low angle faults will affect the heave versus the throw ratio, which in turn may affect whether you get lakes forming in a rift, which tend to require high amounts of throw for heave. So these can go on and affect the sedimentation style as well in places. In the north, we have the Indocinian collision zone, the main Paleotethys collision zone that we didn't see in the south because it was cut out by the strike slip faults. And the Sukhothai terrain overrode Cebu Masu, underwent extensional collapse in the late Triassic, and then this gets sealed by granites. But then in the Cenozoic, this detachment zone, you can just see some of the Paleozoic metasediments here that are in a detachment above Paranices and Orthonices. These get reworked by a Cenozoic low angle normal fault that dips out at about 25 degrees here and gives rise to a metamorphic core complex here. So in the north, we see small scattered rift basins or the large rift basin underlined by a low angle normal fault at the main suture zone. In central Thailand, strike slip faults disrupted that broad suture zone, so extensions concentrated on two larger, deeper basins, and tends to follow this model. The final aspect of faulting style that I'd like to show you is this multi-phase extension. So we have two levels of inheritance. We have the synrift faults, and they can be influenced by older fabrics, and then the younger faults that are influenced by the synrift faults. So these will nucleate, the synrift faults will nucleate in basement. Here we have two different levels of nucleation, and in this particular case, then just the younger faults are nucleating within the post-rift section. So we end up with these quite complex younger fault patterns where there's clearly two directions interacting, and these faults are swinging around and joining the older trends that lie oblique to the direction that the younger faults want to extend in. And so looking at displacement versus fault length graphs, if generally faults have displacement length ratios of about 20:1, we find that the low angle normal faults that are influenced by pre-existing fabrics have low length displacement ratios about 10:1, whereas these faults in the post-rift section have very high length to displacement ratios of about 60:1. So a summary diagram here. We've seen different types of fabrics, some related to sutures that would go through the entire crust, others that are related to much shallower fabrics underlying the rifts. And so we have different levels of nucleation in these fabrics. This one may continue throughout the crust, but if you have a granite that's relatively isotropic in its strength, the faults that will develop in that granite are likely to be different from the faults that are being influenced by low angle fabrics. And so these faults will probably die out and will transfer into different types of fault sets within these granites. And then we have these young faults within the post-rift section here interacting with the deeper faults here. Something I haven't been able to touch on, but I'll just mention it. I've shown granites on these figures, and the impact of intrusions is another factor to consider in this that I haven't had time for, but there's a very complex history and geometry to the intrusions that occur in these areas, and this is an example from the Mogok gneisses in Myanmar, which are part of the Cebu massive terrain, and they're exhumed in the Miocene, so we get to see what these deep crustal fabrics look like in this area. So in conclusion, inheritance is highly complex in this dynamic tectonic setting in Southeast Asia. We're looking at ribbon continents, which give a different kind of fabric and inheritance style to larger continental blocks. We see multiple levels of pre-existing fabric inheritance, and we have multi-phase rifting inheritance to contend with as well. Rift location, orientation, and mode are all affected by the pre-existing fabrics. It affects fault population characteristics, where faults nucleate, and the 3D transfer of displacement across fault sets through the brittle crust. Thank you.
Thank you, Chris. Very nice talk. Bit longer than expected, but we have time for one quick question. Who wants to go first? Henriette, you have one?
You are mainly looking at the brittle field. So my question is about the brittle ductile transition.
Yes.
Is there control by inheritance of this brittle ductile transition, or is mainly the thermal gradient?
Brittle ductile transition. That can vary a lot due to the nature of the intrusions. There's some areas where the intrusions are even of Oligocene age. Other areas where we don't see intrusions, so the brittle ductile transition may be deeper and less affected by young intrusions or young metamorphisms. So it's really heterogeneous, I would say.
Okay, thanks.